So we call this creating condition monitoring platform on the road to vessel autonomy. We have, of course, worked with condition monitoring for a while, but we are on the road to develop the platform, but we're also on the road to vessel autonomy. We have the autonomous vision. Autonomous vessels have been talked a lot about that for the last few years, and there is actually a lot of autonomy ongoing already. The vision is to have unmanned vessels sailing across the oceans, and in some segments it's started already. And we also see that there are different levels of autonomy. We can see it's not so easy to see here, but the very first step is to decision support, actually to provide crew and ship owners with data-driven or data-based information that they can use to improve their performance and also for their assets to increase lifetime and so on. And then we can go further to automate operation of the vessels, and that is already being done. For instance, on car ferries, we have something called auto crossing, which actually there's no it's taking control over the bridge. So when the ferry is crossing from one side of the fjord to another one, it's being done automatically, and then over to the more but there are still people on board these ferries. But the vision is to end up with a scenario where you have less and less people on board the vessels, and then it's of course critical to have a very good condition monitoring system in place. Myself, I work in the intelligent asset management team. We have a portfolio of products, digital products. The energy management is mostly for the ship performance, to optimize the performance of the vessels and reduce fuel consumption, and also to provide information so that the crew and the ship owners can take actions immediately when they see that they don't behave in the way they should be based on their records. Also, and in the autonomous vessel world, that is also very important, because we now can document that, for instance, on the ferries, we see that the energy consumption on average on one trip has been reduced by 25% when we launched the auto crossing function compared to the manual operation of the ferry. Also, the health management, the main topic here, the condition monitoring, knowing the remaining useful lifetime and so on the equipment is critical, especially for autonomous journeys. It's important now, but it's even more important when there are no people on board the vessel. So you should know even better if there is something that fails. Also, it's been a lot of talk about the expert in the loop, or what we call the expert in the loop, to actually have the product experts and together with the data scientists to do the tailored analytics, and also to utilize the product expertise in order to enhance our service for our customers. The basic principles of this for the health management is to optimize the planned maintenance, and that is, of course, I think the aim of a lot of people here today. It keeps the vessel in operation if the maintenance is not required. Vessels, they often have a fixed docking schedule, so that there should be maintenance or overhaul in, for instance, 5 years docking. But if we can prove that this equipment is actually, there's no failures, and you could extend the docking schedule, that is helping our customers to save a lot of money. So, and that is something that we deliver today, to say that, okay, if you can delay your docking with 1 year, then then the customer can save money, and they could also collect their maintenance on different equipments to the same time. For docking a vessel, taking out of operation is quite an expensive thing. Also, to reduce unplanned maintenance, obviously, to reduce the risk of a failure occurring at all, and also again plan intervention when a failure is foreseen, so that they can most optimally plan the maintenance. Of course, there are a lot of challenges when we set up a platform and collect the data and want to have something that the customers and we ourselves can look at and make value out of. So for us, there is a wide portfolio of technology. We have engines and propulsion systems, propellers, thrusters, deck machinery, winches, and so on. So, and all these different elements need to have different types of data and different needs, and maybe also different customers. So, but we also have, it's very varying degrees of digital maturity. Even though we are one company, maybe it's not so long since there were actually different, but there are different locations, different production facilities, and also the product experts are, it's a decentralized, so that they are sitting around in the organization, and when we want to use those resources, they are also heavily tasked. So we need to, I think that's one of the biggest challenges, to actually utilize the in-house expertise, even though we see the importance and the management see the importance, but still I think that is one of the most challenging things at the moment. We also have the customer desire for one seamless user interface. They want to have all the information in one place. If a customer has a vessel with a lot of different equipment, they want to have access information, both with regards to energy management, but also on the equipment health monitoring, so that they can click in and dig down to the different problems on the different equipment. And also, again, the rapid approach of vessel autonomy. There's a lot of development going on, and that puts really high demands on us when we are developing our products, because it needs to keep up the pace of this race, and also to actually put. We should also make money on the way there, because to survive, because we should have a product now that is that we can that makes value for the customer, but we should also see that probably in the near future maybe the business model will change. So the products that we can earn money on now is maybe something that the customer wants or expects to be more embedded in the total package in the future. So our solution is to have one data platform. We are mostly basing on Microsoft Azure, where data are collected from the different vessels via IoT Hub, and then presented in one user interface. We have edge sensor agnostic, so that we are putting out the pre-processing of data to as far as possible, closest to the sensors. We have a data logger on board the vessels, collecting all the signals from the vessel, doing the pre-processing, and sending this data to the cloud. And it's also a question of how much data we should send. If there is a fishing vessel in the Barents Sea that is with quite often bad connectivity compared to more near shore vessels, for instance. We also have a flexible cloud analytics platform. We use mostly Databricks to do the in-depth analysis and algorithm development before deploying into production. And we also have one user interface so that the customers can have everything in one place. And also a little bit on the scalable monitoring is more that we, again, to engage the product experts, it's a challenge, but how to do it in a smart way when we are going from maybe one product range, or say the engines, and then we suddenly want to or need to go into the different products. There are different people involved, and to do this in a smart way is a challenge. But we, as you can see to the right, there is a lot of different products, from everything from diesel and gas engines to different thrusters and propellers and winches and so on. This is a screenshot from the portal. To the left, there is an example from an azimuth thruster, which is one of the main propulsion units on quite a lot of sailing vessels. We can see that there is a warning given here, and it's indicating where it is located. For instance, here on the yellow dot, it's or these different dots shows the different bearings inside the thruster, and the yellow dot shows which bearing is identified as the source of the warning, and we are then producing in this example a vibration FFT spectrum, and we then have an interface so that these warnings are not automatically sent to the customers, because we want to verify those warnings before releasing to the customers. So this warning is going then to our product experts. They get the message that they should go in and have a look on this specific issue, and they have then an interface to categorize and also to write their comments and advice to the customer. So in this case, there is a frequency pattern matching the damage of an outer ring of this bearing, and then they can identify from the trend plots how or to give advice to the customer what they should do. For instance, if this is something that needs to be just help with better lubrication, or if it needs to be replaced in 1 or 2 or 3 months. In the middle, there is a similar example from an engine. Again, one of the cylinders in this engine has been detected, as the plot shows exhaust gas temperature deviation, trend plot of approximately 1 month of data here. And you can see the red line in the bottom belongs to one of the cylinders, which is then deviating more from the average of all cylinders. And again, a warning is raised, and product experts in Bergen, in this case, goes in and do his recommendations. And then when that is done, this warning can be also released to the customer, taking the final decision on what to do. And to the right here, you have it's a similar example from a winch from deck machinery. So it's just to illustrate that we actually do collect data from a lot of different sources inside the same interface. And we do have the challenge in a big company that all the different products or different production facilities are located diversely. So actually having one common place is not something that is I'd say common in the company. We have different levels of analytics. in this case, I call it levels, but it's also on the different levels of complexity. This is an example of trending, baselining single signals from. There's one platform supply vessels, and on each of these vessels there are 4 main engines, diesel engines, and this trend plot shows data from 14 months, and then we take the fuel consumption and compare it to its own baseline, or deviation from its own baseline. So in this case, around 0 is good, and we can see that engine number 1, 2, and 4 is actually quite stable throughout 14 months. But in this example here, we see that there is a decreasing trend, and it's suddenly jumping up at this date. And what we saw, and this is not something that was happening or we predicted or monitored while it was happening. There's this analysis of historical data. So what we saw is that when it jumped up again, that was because there was a nozzle replaced at the scheduled maintenance. But and then it went back to normal performance. But this trend actually could have been detected several months ahead. So in this case, 3-4 months. So if we now instead use this case and set a threshold here, that the performance should not drop below, say, 3% below its own average, then we could say that, give an alarm and say that, okay, action could be taken. And for this specific case, I calculated that the extra amount of fuel that was used by this engine for these 3 months was equivalent to maybe 10,000 euros. So there are some easy way to actually prevent this from happening. And then again, this is only one vessel, and we don't know how many vessels does that occur on. So and then again, of course, as we have seen a lot of examples on, to go further on to machine learning, to actually identify the undiscovered failure patterns, and what we also can do is to not only to detect, but also to use the project experts to categorize these new events, and then we can use their feedback and their classification to train the models further, so that next time it happens something similar, we already know what it is. So, but it's also important that even though we call it levels here, it's not that level 3 is the final and only solution. I think we have to have all of this in one common system. So from the very basic to the very advanced, because there is a lot of information in the very basic, and also in the previous, the failure modes are actually defined by the product experts, and they know what to expect because they have actually experience in what has happened in the past. If we have delivered a thruster for 20, 30 years, we know what could happen, and then they know so the challenge for the data scientists are actually to convert these expected failure modes and into algorithms, and to pick the relevant signals from the vessel. And in these cases, data are actually mostly coming from the control systems on the vessel. So data are there. It's just a matter of selecting the right signals. And again, what we call expert in the loop, the data flow on the vessel is so that to the bottom left here we have the display on the onboard portal. So anyone in the crew on the onboard the vessel can go in and have a real-time look at both the vessel performance and the condition of their equipment, and which is one type of display, and they could take then immediate action if they see also from their own experience that this is showing some bad results. Also, we have some gauges with red and green because we especially when it comes to performance, we compare performance towards the vessel's own history. So after the vessel has run for a couple of months and has kind of covered the different operational modes that it will experience, then we can map up and make the baselines and compare new data to that baseline. And if it's red, then they will see if there is something that they can do to actually improve the performance. The data are also sent to the cloud and put into the onshore web portal. That web portal is also available for anyone with the internet connection, so it's so it can be used mostly in our cases for the customers sitting in the office or maybe having a fleet of vessels and the ship operators, and they can then easily see both if there are some vessels performing badly and also get the alerts on the condition. But again, the expert in the loop is very important here, both for us to actually continuously improve our product, but more and more to have as a service for our customers, because they when they start to see the value of the data, they will more and more come to us to actually ask for tailored analysis as well. Especially or typical scenario is that when they have our system installed, then they suddenly discover how they actually operate the vessel, and then they can take some immediate actions, and then they can kind of tune and save a few percentages already just by being knowing what's going on, or what they with some simple means that they can take action. But also maybe after a while they can come to us and ask for more tailored analysis. What if I upgrade my vessel? What should I do next to save more money? If I throw out the diesel engines and put in some batteries instead, will that make me save more money? And change propulsion system and so on. So there could be some kind of vessel configuration update, and that is something that we have seen quite often now, and especially when there is more and more focus on reducing emissions, it's more and more demands on this, and also in the internal loop. So yeah, to summarize, what we have is a quite flexible platform, and we put the sensor agnostic interface, which provides compatibility with a quite diverse range of products. And we also deliver these services to what we call the OEM late adopters to the digital journey, to actually give them a capability to progress quickly, and a cloud platform which is good both for our customers but also internally to share data and share analysis and get feedback from product experts. And again, back to the starting point, actually to understand how the equipment will fail and when it will, that will allow us in the end to de-risk the autonomous voyages, which is the final goal for the maritime industry.
Thank you very much. Thank you. Thank you.